I want to talk about a reaction today called free radical halogenation. And this is the reaction of a halogen like chlorine or bromine with an alkane. So for instance, if we look at a very simple version of this reaction, where we react bromine or chlorine, that's our X, with an alkane. In this case, we're talking about methane. In the presence of light, we need light or heat to catalyze this reaction. We use light more often than heat. We'll get the alkyl halide plus the haloacid. This reaction is only really practical with chlorine or bromine. Now, in order to understand the mechanism of this reaction, there are a couple of important facts that we need to consider in order to help us explain how this reaction works. First, the light interacts with the halogen. So light interacts with X2. It doesn't react with the alkane, it interacts with the X2. The second is that the quantum yield of the reaction is much greater than 1. So what is quantum yield? Well, it's given the Greek letter phi as its symbol. It's equal to the number of molecules of product for every photon that's shown on the sample. So if one product molecule is made for every single photon, it will have a quantum yield of 1. The fact that we have a quantum yield much greater than 1 means we get a lot of product molecules for one photon. So our mechanism, whatever it is, has to be consistent with these two facts. So let's look at a mechanism that is consistent with this. And when we say draw a mechanism or show a mechanism, we're talking about using curved arrows to show the movement of all electrons in the reaction. So for this mechanism, the first step is light reacting with my halogen, diatomic halogen molecule, giving me two radicals. So in this case, if we're looking at using chlorine gas as my halogen, I am going to split the chlorine gas into two chlorine radicals. These single-headed electrons show one electron moving to each chlorine to give me the chlorine radical. In the second step, one of my chlorine radicals reacts with one of the hydrogens on methane to extract that hydrogen, giving me, in this case, HCl and a carbon radical. So again, I'm moving one electron at a time. So I'm showing this electron reacting with one of the two electrons in this bond to give me HCl, and the other electron ending up on the carbon to give me this carbon radical. So that's the second step. Now, in the third step, you might be tempted to say that this CH3 and this Cl come together to give me one molecule of product. And I'm going to show you in a minute why that's not the case. The next step is actually this one, where my alkyl radical, in this case my methyl radical, reacts with another molecule of Cl2 gas to give me a molecule of my product and a chlorine radical. So this gives me one molecule of my product, but importantly, I'm left with a chlorine radical. Why is this important? Well, this chlorine radical can actually go back to this first step, or the second step, I should say, and it can do what this first chlorine radical did. It can take a hydrogen from this methane and give me a CH3 radical. And then this CH3 radical can go back to the third step and extract a chlorine from my chlorine gas to give me a product and a chlorine radical again, which can go back to the second step, which can do the second step, which can go back to the third step. So I get this loop. This is a chain reaction. It goes over and over and over again, giving more and more product. That's how I can get many products. I can have quantum yield that's greater than 1 from a single photon of light. I get this chain reaction. If we look at the other possible way of forming a product, where one alkyl radical and one chlorine radical come together to form my product that does give me a molecule of product, but it doesn't give me a chain reaction. One photon, in this case, gives me one product molecule. It doesn't give me a quantum yield that's greater than 1. So on your exam, on your quiz, you're going to be very tempted to write as your third step this one right here. Don't do it, because this is going to be wrong. You want to make sure you pick the right steps. Now, we do have names for these steps. So for this first step, we call the first step the initiation step. This initiates a reaction, it starts a reaction. For the second step, propagation step 1, because it's a step that propagates the chain reaction, it keeps the chain going, and it's the first of these propagation steps. We call the last step in the formation of our product propagation step 2, because it's the second step in the propagation of our chain reaction. We call this step right here, where two radicals come together, a termination step. We call it a termination step because you'll notice no radical molecule or atom is made in the step. It stops our chain reaction. It terminates our chain reaction. In fact, this is not the only termination step. Any step where two radicals come together is a termination step. So this reaction where two methyl radicals come together to make a molecule of ethane is a termination step. Also, where two Cl radicals come together to form a Cl2 molecule with no radicals on the product side of a reaction, that's also a termination step.